All right, let's get started. So we'll just glance at the syllabus to see how we're doing. So this week, we need to finish up a little bit from last lecture. So we'll go over the alkene reactions. Then we'll switch over to transition metal chemistry. So this is kind of more fun fact, the chapter, but we'll do some field theory. And then week 9, we'll go back to OChem, so alcohols, aldehydes, ketones, carboxylic acids. And then we have some fun labs. So Thursday, we'll be doing a radioactivity lab, so that should be really fun. Next week is a one-pot synthesis, so this is super fun as well. Then we'll end with polymers and biochem, and definitely don't want to miss lab that week, so that's aspirin synthesis. And that brings us to the end, basically. And welcome, welcome. I see many of you are online today. All right, any questions about the end of the year? And then don't forget about your paper. So everyone should have gotten revisions back from me. If you haven't, just let me know. I think that's about it we have for the end of the quarter, just the paper, and then obviously our final exam, which will be the usual review Tuesday, test Thursday. All right, let's finish up our OChem chapter then. And so alkenes tend to be a bit more reactive than alkanes, and so they have this double bond here. And so they tend to undergo hydrogenation, and so you can test hydrogen gas over them, and then using some sort of usually palladium platinum catalyst, you can hydrogenate. And there are different like molecular sources of H2, so you can do this in the bottle type reaction, pretty simple. And so they also undergo halogenation across this double bond, so you could add, in this case they added chlorine, but you could add like iodine or bromine is also used for halogenation, and so that adds across the double bond. And so if it's a halogen, then you get the addition of both to that double bond. And so looking at this, so you can get different products. So if we have E-butene, then the way it's going to add, so you make this bromonium intermediate first with your halogenation, then that blocks one side, so then the other bromine has to come in from the bottom, and then that would push those electrons up, and so that's why you get the anti-addition product here. So looking at stereochemistry, those bromines are anti, so across from each other, and again that's from the mechanism of reaction. So they're not on top, right, because again you form this bromonium intermediate, so that physically blocks that top face, forcing the bromine to come in from the bottom, again giving you the anti-product here. So some things to think about for OChem too. And you know, I overhear people talking about that you might have to take OChem, so use your molecule kits in OChem as well, so you can kind of visualize these intermediates if they're not apparent to you. And so here's just the mechanism shown broken down, what I was talking about. So double bond, the electrons attack your halogen first, so just doing bookkeeping of electrons, and so you form that bromonium ion. Obviously that's unfavorable, having some sort of halogen with a plus charge on it, and so that means the other halogen, in this case our bromine, it has electrons, and again it has to come in the opposite direction since your other bromine is blocking that side. And so it doesn't matter which one it adds to, there, but then that forces those electrons off, so again resulting in the anti-addition. And so technically you could get these two different products, but they're the same by rotation, so you just get one product. And so now looking at Z-butene, so now that's a little different. So if we analyze this, so Z means the same side, so our cis isomer. So then if we imagine, so our halogenation reaction, again we have to form our intermediate, either the top or the bottom. And so either way it blocks that face, and then the other bromine, so let's do it just on the top for simplicity, so we can walk through this. So bromine, bromonium intermediate, that forces our other bromine to attack from the bottom. So that forces that up. And so what we have drawn is this product here. So bromine comes up, methyl group goes up there, and so bromine is here. But then if you drew it from the other way, so if you started bromine on the bottom, again, bromine attacks, then you get a racemic mixture. So they have different chiralities. And so if you were to try to like superimpose these two, they would not be the same. So that would probably be more clear with a molecule kit. So if you rotate, let's see, like this bromine, you bring it down, and then that means that the methyl group, though, is going to be on the other side. Do you all see that? And so I don't want to spend too much time on it, but get a kit. And so we have molecule kits too if you want to like borrow them or explore, check them out. So if it's not totally obvious, and again, it can be difficult to see, but get a molecule kit, right? Draw these two structures out, make them, and then you can play with them and kind of convince yourself, yes, you would get a racemic mixture. These are not the same. And so this just walks through, again, the mechanism in more detail. And so whatever side we formed our ion on, then the bromine attacks from the opposite, and so in this case resulting in the racemic mixture. So other ways you could get racemic mixtures, so you could have cyclohexene. And so cyclohexene, notice that this is kind of reactive. So you can compare it to like cyclohexane. So cyclohexane, right, would not have a double bond. And then don't confuse it with benzene either. So remember, benzene kind of gets totally new properties, and now we have a fully aromatic ring here. So now this tends to be a lot more stable. But cyclohexene is pretty reactive. And so you could do what's this bromination, and then if you do a hydration to this, instead of adding 2 bromines, what you get is 1 bromine. So then you would make your intermediate. And then just like before, now the water has to either add from the opposite side. And so this case, depending on which side it goes to, you get the racemic mixture of either OH is up if it goes from the bottom, or the OH gets on bottom if bromine comes from the top. So you could draw out, again, similar sort of intermediate. And so now, right, planar intermediate, and then OH either goes from the top or the bottom. So similarly, you can make 2 different products here. And so first, we add our chlorine, so we make our halogenation reaction. So now, intermediate species here. And so notice the hydroxide now is going to go to the more substituted carbon. So you have kind of 2 potential ways for it to add. So you're looking at it, and it could maybe go here or go here. However, this is more favorable since there's more carbons attached to it, so it can stabilize this reaction here. So it's going to go to the more substituted carbon, except again it can attack from 2 sides, so it's either can go from the front to give you this product, or if it goes from the back, then we can get our other product. So again, in this case, we would get 2 different stereoisomers. questions? And this is just the explanation for why it attacks that one, since, again, that stabilizes our intermediate plus charge better. Okay. So now we can look at hydration. So you can also do this hydration across the double bond. And so looking at it, so once again, we look at this product. So now, what's going to happen? And so let's look at the mechanism as well. So first step, so now we have our double bond attacking our hydrogen. And so you could technically, right, make two products with this. So that's the question, where's the hydrogen, where's the plus charge? And so same sort of principle applies like we looked at before. So the plus charge is going to be stabilized on the more substituted carbon. So this goes ahead, right, just account for your electrons. So this made a new bond with hydrogen. That left this carbon as electron deficient, so it has a positive charge right now. And so it's just hanging out. And so that's why, again, that's more favorable, because otherwise, if we had added the hydrogen to this side, we would have been left, right, with a positive carbocation here. That's not as stable, and so that was not as favorable. And so we were here with our intermediate, so that means water is going to go ahead and attack, and then you'll deprotonate. And so that gives us, again, the more substituted product of the hydroxide on that carbon. And so you'll see this term as if you move into OChem or take OChem. And so this is called the Markovnikov product, and that just means that it adds to the more substituted carbon. And sometimes you'll see other mechanisms where it's called anti-Markovnikov, where it favors the least substituted for some reason. Let's see, I think, oh, no, one more page. No, not that page. This page. So last more bit of reactions to look at. And so benzene doesn't really do too much, but you can force it. And so let's just define kind of an aromatic. So aromatic compounds, how if I could spell? Redo that. Aromatic. And so sometimes they smell nice, but sometimes they smell really bad, but they really refer to anything with a benzene ring. And it refers to, again, your delocalization. And so often abbreviated like that or like this, implying you have your alternating double bonds. And then just thinking back to MO theory, so the reason why it's so important is you have all those pi, your p orbitals, so we could call it probably pz, right, going up and down. And so they're all in phase with one another, and so you can have that delocalization, right, and your electrons essentially running around that whole ring. So that makes it super stable. But you can still have some substitution reactions, especially with like substituted benzene rings. So for example, let's just say you started with that compound. And so that's probably just called bromobenzene. Let's double check that. Yeah, so this is just named, I was just making sure it doesn't have other names. So bromobenzene, so that's pretty straightforward. But then these aromatic rings can undergo electrophilic substitution, and so sometimes you'll do like a nitration with nitric acid, for instance, and then make different nitro substituted. And so you can identify them by where they substitute. So depending kind of on your groups and what you're adding it to, you could make what's called the ortho product, and that's when it's right next door to whatever your other substituent is. And so just and so this would be called like ortho nitrobromobenzene. And that O just indicates the ortho position. And so they have to be ortho to each other. So you know, again, your nitro group is right next to your bromo. If you did the meta substitution product, and so let's just draw out an example. And so meta is now 2 away, and it could also be on this side, right? They're the same by rotation. And so now to name it, you just put the little m, and it would still be nitrobromobenzene. And then the last one, if we had made the para-substituted version, and that would just be p-nitrobenzene, or nitrobromobenzene. But you might also see other terms used, so this could also be labeled, so we could call it priority 1 here. So if this is 1, 2, 3, 4, so then you might see interchangeably, right, 4 nitro, 1 bromobenzene. And they mean the same thing. So it's just whatever bottle you happen to be looking at, same thing. So same with this one, 1, 2, 3, we could call it 3 nitro, 1 bromobenzene. But you'll see all sorts of combinations. And so I just pulled up one as an example. So again, for some reason, Sigma Aldrich names it 1 bromo, 4 nitrobenzene. Sometimes, I mean, they may even swap the numbers, because sometimes people number the priorities different. So just be aware. And so with that, now is probably a good time to mention, so that's why chemists have the CAS numbering system, because the CAS number is consistent. So if you're ever confused and people use different names, you know, just go by the CAS number, because that will always be consistent. And then the last bit are some other kind of aromatic substitution reactions. But again, these are pretty forcing conditions. For instance, you can take like a bromine and then add to it a catalyst, so like iron, depending on whatever X is. So that could be iron tribromide if you were using bromine. You'd want to keep the halogens consistent, otherwise you might get a mixture. And so I'm not sure of the mechanism of this, but some sort of iron catalyzed substitution reaction, so adding your halogenation here, and then forming HBr or whatever halogen. And so here's just, again, another nitration condition, so very forcing, so you're doing nitric acid and sulfuric acid to get that nitration reaction to occur. And if the benzene is substituted, it's easier to do different reactions, but just pure benzene requires pretty forcing conditions. And so same thing, you can add a sulfonate group to that, but again, very forcing conditions with sulfuric acid. And let's see, we'll throw in just more common things. So for instance, this compound, so it has a methyl group on here, aromatic. This is pretty common, so this is the solvent known as toluene, and so that's used a lot. It's relatively safer, like compared to benzene, I think. And then we also have, so if we had put an amine onto our benzene ring, so these are called anilines. And of course you can have ortho, meta, pair substituted aniline. So these are super common, especially in like, you know, drug development or catalyst development, some sort of aniline to add this aromatic ring to it. You can also make all sorts of like linkers, which make it convenient for synthesis. And so usually you have a bromine at either the meta position or the para position, or the ortho, really. So it could be either one, and then people like to do substitution depending whether you're going for like this kind of bite angle, or if you want a larger bite angle, you can kind of pick your substitution. So those are nice building blocks. And then we'll probably get back to this later. Well, let's first write out, sorry, I forgot phenol. So this is also super common, is phenol. So that just means you have an OH substituted on your benzene ring. And we'll, like I said, we'll probably revisit this one on our last week when we go back to organics. But I just want to show it. So then you have benzoic acid, which would be our benzene base, right, acid form. So notice the carboxylic acid group. So that characteristic, double bond O and OH. And remember, right, this is the acidic proton that pops off. And then not to be confused with benzaldehyde. And so benzaldehyde just has the aldehyde group, and so that's just that CO with a H there. So no OH. Right. Questions about this chapter? So now let's switch gears to what feels like more fun facts. Fun facts and chapters. And so your next chapter kind of introduces transition metals and gives a lot of trivia. And so I appreciate that, but, you know, at the same time, you don't have to know everything, you don't have to memorize everything. But then we also want to appreciate like research topics. So for example, they kind of didn't say too much about scandium. And scandium tends to be difficult to work with. I didn't put a periodic table, did I? Sorry, I was trying to see where I put a periodic table somewhere. Okay, I'll grab a new one. But scandium, so all these tend to be difficult to work with just because the early transition metals have, you know, pretty low D count, so they can be really sensitive and kind of finicky. So we're starting with scandium over here. And well, let's take a look at it while we're looking at this page. So this is our P table again. And so let's go back to its electrons for a second and how we kind of treated things in the past versus how transition metal chemists tend to think about these compounds. And so if we look at this, right, we were used to just treating it in its ground state with this 4s2, 3d1, right? We recall that from filling up the pattern. So we would start on this row, and this was our S block, and then this started the 3Ds. Does that sound familiar to everybody? All right, so we remember that, except when these things are actually in compounds and how they really behave is better reflected by their D count. And so generally what we do is, so looking at the number that they're under, that's just what we consider their like D electron count. So even though, right, again, going back to what we did first quarter, right, we treated it like this. We said, yes, it fills up the S first. In practice, these electrons are actually in the D orbitals with compounds, and so we commonly just say scandium is D3. And so let's look at then the types of reactions and how it tends to behave. So since it tends to behave as kind of this D3 compound, you tend to find it, at least in starting materials, as like a trichloride or some sort of scandium 3+ compound. And so these are kind of cool and pretty relevant since they were found to activate nitrogen. So let's see what they did. So if you reduce it, and so this is a trick that chemists use to kind of capture these reduced species. And so this is CP star lithium, which, so CP is this, it's just like an aromatic ring, except instead of 6 carbons, it has 5 carbons. But then CP star, and why people prefer CP star, is it's bulkier, and so it tends to kind of be more stable, kind of more capping, so you can kind of see, right, these methyl groups kind of cap it there. So that's CP star, and it's also benzene. So when we think about benzene, now we're thinking about it acting as a ligand to some metal and how it interacts. And so each one of these double bonds here can kind of donate to this metal. And so we say that this is 6 electrons basically donating to the metal. And so CP then is a 5 electron donor. I'll just put here L2X, but this is more for ligand classification, not as relevant right now. But then what's really cool, and then we also have this group over here. So these kind of bidentate, these are called like bidentate ligands. And they're called bidentate since it's two kind of arms there biting. And so dentate just kind of means it's coordinating. And so they use these kind of amine-based ligands, and notice their difference in electronic structure. So one, sorry, I drew that poorly. So they have some sort of difference where one is a double bond, one is a single bond, so they're donating different amounts of electrons technically. So that means that this one is probably donating 2 electrons, that's donating 1. So that's often used a lot in these types of metal compounds. But then what's cool is, so you made this sort of intermediate species, so they're held together by the chlorines. And then what was nice is they were able to take this compound and they reduced it by 2 different methods. So both in the presence of nitrogen, well, this kind of gives you an idea what people use. So you can use, and I would have to look back at the paper to see what form, but either they use like potassium metal, or sometimes you can make this compound called KC8, which is just like potassium intercalated in carbon, but it's easy to weigh out. It's like a bronze powder. And so they reduced it, and then that binds nitrogen. So that's really exciting if you're doing research. And so the whole goal of this is to eventually do like the Haber-Bosch process at room temperature. So if you can activate nitrogen, that's a good first step, since nitrogen is really difficult to activate. And so then it looks like they were able to do some other functionalization. And so ideally, again, you'd want this leaving off as some sort of ammonia-based compound, but that's more difficult to do. And so again, that's pretty cool, these intermediate nitrogen species. All right, so let's move over now to titanium and look at what cool reactions it does. And so titanium, you might be familiar with it with titanium dioxide. So do y'all remember the hubbub of titanium dioxide? The curtain? Oh, yeah, the air curtains. I know what you're talking about. You are correct. So they do that as well. Well, that's not the piece that I was thinking about, but that is a good point. So if anyone remembers, do you remember when we watched like the silicon tetrachloride curtain, but then we weren't sure if it was silicon tetrachloride, but titanium tetrachloride does the same sort of thing. That's actually shown here in this reaction. So this is sometimes called tickle, and it reacts with water. So we could try to find that video if people don't remember, but basically you release that in the atmosphere, it reacts, and then makes that kind of white curtain and HCl gas, so that's fun. But then titanium dioxide, why I brought it up is because it was in the news recently about Skittles, that it's in Skittles. And it's really in a lot of things. That's why I thought the news thing was kind of funny, because they were talking about how carcinogenic it is. And honestly, I'm not sure how valid or not that research is, because titanium dioxide has been used in so many like food things forever. So it's not just in your Skittles, it's in a lot. And especially if you have like white products or like, I noticed it's in like vegan cream cheese, like that's how they get it super white, is titanium dioxide. It's also used in sunscreen, so it's really good for sunscreen. So it's like, you know, literally white and physically blocks the sun rays from getting to you, so it's pretty effective as a sunscreen. I've also seen it used in like water purification, and it's good at like, if you add it to water, it'll kind of coagulate with everything and cause sediments to sink to the bottom. But yeah, I'd be curious to know what the carcinogenic research shows. Question mark. I feel like everything causes cancer, though, allegedly. I think that's all I want to say about titanium for now. And so vanadium, as we start kind of moving over, I lost my periodic table again. And if you have any chats, comments, questions in the chat, don't be shy. So now moving over to vanadium, so this would be more known as D5 for transition metal chemists. And vanadium's still pretty tricky to work with, but you start getting more interesting chemistry there. And so what I kind of mean by that is you get these fun colors. So this was from your textbook, but this is solutions of vanadium-2 pentaoxide, and it makes different species at different pH values, so very pH sensitive. And so that's kind of cool. You're going to see these fun colors. And we'll talk about, well, where do the colors exactly come from as we dive in. Chromium is a super fun one in catalytic chemistry, but still kind of difficult to work with. Again, just because of the nature, these would still be considered like early transition metals. So D6. And so you can also use chromium for like bubblers. So this is a chromous bubbler. And so that's used to react with oxygen. So if you were trying to do air-sensitive chemistry, and usually your tank is good enough, I'll say that. So usually you buy these tanks, and if you run them off a liquid nitrogen tank, usually you don't have issues. But sometimes if you're doing something sensitive, you need to pass it through an additional bubbler. And so you can just use a chromous bubbler, and then it will react with the oxygen. And you have zinc amalgam at the bottom, so zinc mercury, and then it bubbles through, and then out comes deoxygenated gas. Chromium also does fun colors. Let's see. So manganese, most people are familiar with it with the potassium permanganate. And so that's an oxidizing agent. And so it's also used as like a TLC stain. And so how it works is it's reactive to double bonds. So if you have some sort of double bond, then it will oxidize it. But if there's no double bonds, if you form the alkane product, right, there'll be no reaction. And so this is a quick way to test to see if like your hydrogenation reaction is complete or if it worked. And so you take your little reaction mixture, spot it on a TLC plate, dip it in your manganese, and if it shows up and turns like brown, then you know you have some sort of alkene product. If it doesn't react, then you made the alkane. So that's really helpful. And so next we're looking at iron. And so iron, you can see it present in a lot of minerals. So magnetite, iron pyrite, so hematite, all those are pretty famous. So iron pyrite is of course an iron sulfide compound. But it's also a workhorse in terms of catalytic chemistry. So there's all these class of compounds that involve iron, and they all bind nitrogen, so that's really cool. And so these have been pretty prominent in research. And so if you look at it, And so these would be called tridentate ligands. So again, just now we have tri, so 3 things binding to our metal. Although technically you could argue it's tetradentate with the silicon and bromine, but people usually just kind of look at your arms that are hanging off of it, call it tridentate. And these are pretty famous, this class of tridentate ligands. And so people have made all sorts of little variations, and you can see the general idea, you know, some sort of other atom, so either bromine, silicon, or carbon, and then your little tripodal. And so notice what I was saying, that they put it in the ortho position to have that correct kind of bite angle so it goes up and is able to bind to that iron. So this was all done, right? Someone designed this going for that right bite angle, and also that's convenient synthesis-wise. And you can see, right, they repeated this. It's pretty easy to modify. Notice what people do is they also change like the arms on these phosphorus groups. And so isopropyl, so this is isopropyl here, IPR. So remember that. So each phosphorus, right, has 2 isopropyls on these. So that's fairly common. People swap them out for methyls or phenols. So you can see they use phenols in that one. So phenyl just means a benzene ring, basically. You could also do, what's it called, tert-butyl, but tert-butyl is usually too big, or it doesn't make it to prime time. So that would be a T-butyl group, but the T-butyl groups are super bulky, so maybe they end up blocking reactivity. And so, of course, iron, though, how it's generally produced is from these iron ores, and then you react it with CO at very high temperatures, and then you get out your iron, and of course CO2 is a byproduct. And so here's just the furnace of that, where you would have your iron ore going in, and then of course it gets super, super hot. Molten iron can come out then, and then your gases degas. So let's see, continuing more fun facts. So cobalt is another fun one, and this is another kind of workhorse of transition metal chemistry, so people like cobalt a lot. And so now this would be considered D9. Remember looking at our 9, even though we would fill it up right 4s2, 3d7. Again, it behaves as a D9 compound. And so chromium has a lot of pretty colors too, or cobalt, sorry. Cobalt has a lot of pretty colors, so cobalt oxide is this nice pretty blue, and so that's used in like stained glass windows or ceramic coloring. Cobalt phosphate, so that gives a lavender pigment. Cobalt sulfate, that's used in like batteries and also glazes. And there's also fun like cobalt compounds. And see, so that brings us to nickel. And so nickel tends to get a lot of fame for its catalytic reactivity. And so if you look, so, right, platinum, palladium, these are your standard like catalysts. Usually everything is either platinum or palladium. And so nickel can also do some work. Except the problem with nickel, so these tend to be nickel 2+ species, and nickel 2+ tend to just go undergo 1 electron processes. So that means, right, they're only able to add or gain 1 electron at a time. So this is part of the limit with catalytic reactivity. Again, we're not entirely sure why, but like palladium, platinum, they tend to go like 2 electron conversions. So nickel's just 1, and then if you're thinking about like, making sugars or CO2, those are going to be 6 electron processes. So that doesn't quite match up, so that's why it's kind of difficult to do that, at least synthetically, with these man-made base, I guess, catalysts and analogs to what nature does. And so this is just showing, again, what nickel does, so highlighting kind of these 1 electron processes. So we add an alkyl group, so it adds an X here. Then we can do our substitution reactions. But again, just 1 electron at a time. And so these also can have fun colors. They're generally green or orange, the 2 colors that nickel tends to be. And then, so now looking at copper. And so I think most people know that the Statue of Liberty is made out of copper, but of course, right, it's green since it's reacted with all the water in our atmosphere, and so it's now copper hydroxocarbonate and copper hydroxosulfonate. So that's why it's green. Oh, it's probably better for it that it's nice and green and protected. And so copper also can undergo different colors. So we've mentioned this before. So for example, copper 2 sulfate pentahydrate is blue. But then if you dehydrate it and just make pure anhydrous copper sulfate, that would be a white powder. And then copper's also used with zinc. So copper plus zinc, so that makes brass. And so that's another big use for copper, is being used in brass alloys. And so of course, right, zinc does that. And you're also aware that zinc is used for metal coatings. So we discuss that a lot in our Echem chapter. And let's see, zinc oxide is also used as a mold inhibitor and also used in photography. So that was copper, zinc. And so now we'll look at gold, and our 2 of our metals here. And so gold is back in group 11, so this is considered D11 with, again, how it behaves. And so these tend to just make either 1+ or 3+ ions with gold, so they behave kind of similarly to silver. Gold is also a big catalytic workhorse, so you can get it to do all sorts of catalytic transformations just because it's gold. And the lower elements will not do that. I'll try to pull up a paper on gold so you can see. So let's see. So gold stannate, that can be used in like ruby glass. What else is gold good for? Other than catalytic compounds. So let's look at, we have on here silver as well. So silver iodide, silver nitrate, silver oxide, silver bromide. And so notice what they are involved in. So of course you can do mirror plating with them. I'll try to see if I can do this demo for y'all. But if you notice, they're also involved heavily in like photography. So again, more photography. And so silver compounds tend to be light sensitive. I'm not entirely sure why, but you generally see silver compounds stored in like a dark amber bottle to try to prevent as much light as possible from coming in. Yeah, that's pretty unique to silver, where they're sensitive. And let's see, so last, not least on this fun fact, of course, is mercury. So mercury is relatively inert, at least just elemental mercury. So I think elemental mercury kind of gets a bad reputation. And so that's pretty, again, relatively safe. Mercury, so chloride, this is used as, or at least it was used as a preservative for food, or wood and embalming, sorry. And used to use it in pigments, although I think they also use like mercury in makeup back in the day. I think that was toxic. But not to be confused with like organomercury compounds. So organomercury compounds tend to be toxic. Probably the most famous one is methylmercury. Has everyone heard the story of methylmercury? It's always like the horror story of chemistry that everyone tells. So this one researcher was working with methylmercury and got like the tiniest drop on their glove, like barely even knew about it. And then several months later, this researcher started having like neurological issues, and then they died. And so it's just super toxic. And what happened is, as an organic, now it can just quickly pass through your bloodstream. So the researcher didn't even know that they had that much contact. But even if you had known, it's difficult to chelate mercury once it's in your body, so it's really difficult to detox. So I'm not even sure if that person could have been saved if they had known from the beginning. So that's a famous one. And so it's used as a methylating agent, or at least it was, but there are much better alternatives, you know, methyl lithium, methyl iodide, all these are much safer than trying to use methyl mercury. And so let's look at other things. Oh yeah, so I put a link in the notes about organomercury. So that's in there. Oh, I don't want to look at sad stuff too much though. So let's see what fun you can have with mercury. Internet is super slow. Any day, this YouTube will load. And so going back, while this thinks about its life, let's look back at these notes for a second. And so what I was kind of alluding to as well is, so you have to be careful. And really
$69 US Special Forces device turns men into beasts. This Marine Corps officer is bringing military technology to the public by inventing a device that emulates 54,000 crunches in 20 minutes and builds an incredible six-pack up to 10 times faster than regular exercise, allowing you to get ripped in just a few weeks without working out or dieting. Here's how the story began a few months ago. Captain James Snipes is a 32-year-old US Special Forces officer and a bioengineer. He had dedicated his life to serving his country and was always on the front lines, putting himself in harm's way to protect his fellow Americans. But during one fateful mission, James' life changed forever. He was leading his unit through enemy territory when they were suddenly ambushed. In the heat of battle, James was struck by enemy fire and suffered severe injuries. Fortunately, James' unit managed to secure the hazardous area and evacuate him to the hospital, saving his life. He spent the next 3 months in a hospital bed healing, determined to return to the front lines and serve his country again. But when he finally recovered, he realized that his body was still weak and he wouldn't have enough time to get back in shape for the critical next mission. He knew he had to find a way to get back in shape fast. That's when James remembered what he learned in the army about using electronic muscle stimulation to help muscles grow, and had a desperate idea. Using the EIMD phenomenon that powers all the muscle tissue growth in a human's body, he built a revolutionary device that uses military technology and an innovative type of stimulation to ignite rapid fat loss and explosive muscle gain. Having only 3 weeks left.
This video has been sponsored by NordVPN. You can get a special deal and support the channel by visiting nordvpn.com/NileRad. Over the years, I've worked with Mercury many times, and it's almost always a bit of a pain because it requires special handling as well as waste management. But despite this, I think it's still slowly becoming one of my favorite elements. Small amount of mercury, and then I pulled out my small piece of sodium, quickly dried it, and threw it in. I was kind of...
Oh yeah, there's my criticism of this procedure. So notice that he started with mercury at the bottom and put sodium in. I would do the opposite. So put your sodium and then squirt your mercury on top. And you'll see why. There's just a delay here.
Nervous that I'd immediately get fire in molten sodium, but nothing happened. The major reason for this seemed to be that the sodium was just a bit too tarnished and it prevented it from coming into contact with the mercury. The sodium's also way less dense than the mercury, so it kind of just floated on top, which didn't really help either. To fix this, according to some procedures that I read, it's pretty common to use something like a glass rod and to shove the sodium into the mercury. Then once it's underneath, it can be scraped and crushed to expose the fresh sodium. So I decided to try this, and initially I still had some trouble getting it started, but then suddenly there was a little thump and all the sodium instantly disappeared. Then when I mixed it around a bit, I noticed that the texture of the mercury had also changed. The reason for this was because as the sodium combined with the mercury, it didn't do it uniformly. The reaction was extremely fast, and the mercury that was around the sodium took up most of it and got a relatively high concentration. And when the concentration of sodium gets above about 1% by mass in mercury, it starts to solidify. So what this gave me was a bunch of solid sodium amalgam mixed in with some regular liquid mercury. However, after I let it sit there for a few minutes, the sodium slowly dispersed evenly throughout the mercury and most of the solid bits disappeared. It kind of went back to more or less looking like regular mercury, but the one major difference was that it was now sticking to the glass a bit. I then continued adding more sodium, but even the next one didn't result in any fire or sparks. On my third run though, I used a slightly bigger piece of sodium and I managed to get some fire. I couldn't find a good reference for exactly what was going on here, but then again, I don't think it's too complicated. As the amount...
Okay, so that's basically just what I wanted to show you. I'm not sure why he was getting fire. I'm not used to seeing that, but yeah, like he was explaining, you know, you drop it in, it kind of cleans the surface too and just primes it. And I never had that issue of it like not dispersing. So like I said, if you put it sodium first, then drop your mercury on there, you get a little poof like he mentioned, or he said it kind of went boom. I usually see like a little cloud of some gas, which now I'm not sure what that gas was, but kind of cleans it, poofs it, and then you're ready to react. And then you would have it kind of in your vial, and then you can pipe it over your reaction to your sodium amalgam. And then what's convenient is once the reaction's done, all the sodium or potassium is used up and you can recover the mercury. That's nice. All right, so I think that's kind of our fun fact section. And now we're going to dive into the electron configuration a bit more and then try to explain naming and colors. Let's see how far we get. And so now we're just kind of looking at our periodic table again. And so just comparing from the electron configuration that we kind of did earlier on when we just filled it up, again, based on what we expect versus how we treat them. So again, their D count just matches their number. And so we can say titanium is D4, zirconium is D4, ruthenium D8, etc. So you can kind of look at that and again just compare. So this again is reflective of their behavior in transition metal compounds. So that's the discrepancy. And so d electrons in group 3 are readily removed via ionization. So we saw that kind of with our scandium trichloride compound, so that's why it exists in that form. And then so if we look at group 11, so now this goes to, right, D11 compounds, but they kind of tend to behave as 1+, so we see them a lot, again, in their 1+ oxidation state, especially with silver, right? Silver compounds are always 1+. We see copper is usually 1+ or 2+, and then gold is either usually 1 or 3. And so now this is just comparing what the D count is for these different 2+ species. And so looking at zinc 2+ now, so if we look at zinc, the neutral compound is 12, so then if we lose 2 electrons, that makes it a D10 compound. So skipping to nickel, so nickel 2+, that's a pretty common species. And so again, nickel, the neutral form is D10, then it loses 2 electrons. We consider it to be D8. So same thing, so looking at iron, so iron neutral, D8, iron 2+, D6. Continue that down. So we'll look at, we'll just end on scandium. So again, scandium 2. So now that one, again, D3. So 2+ leaves it only as D1. And so then I just kind of redrew our orbitals, which might help us later as we talk about things. So these are just our d orbitals. So primarily, if we're looking at compounds reacting, they're invoking the dz² orbitals a lot, since these ligands on the octahedral complexes can go on the top and bottom to bond. Then you have your donut ring where they can bond with. And so same thing with the x² minus y². That's all prime for bonding. But we'll look at these. And so looking at a compound, again, the difference, and this again explains why we call this D8 versus the metal. So in our gas phase, so when we're figuring out our electron configuration, the s orbital is below the d in energy. And so again, that gives us the electron configuration we're used to. But then once they're complex now, these d levels are now below the s orbital, and so they get filled up. And so that's just because they're involved in bonding. And so, right, looking at this, it's going to be invoking some dz² and probably part of these orbitals as well in bonding. And so that change brings those d orbitals lower in bonding. And so all this is saying is then if you have the oxidized metals, right, start with your group number with the neutral and then figure out your D count. So in this case, looking at our nitrogens here, so all these are donating 2 electrons. So I just put the full arrow so we can see that. So the nitrogens are donating 2 electrons each. And that means it's an L-type ligand. So you see I've used that denotion again. And so this just means neutral. So neutral ligand donating 2 electrons, so we don't have to worry about it when we analyze our oxidation state. But then if we look at chlorine, so chlorine would have a negative charge, right, chloride. And so now, since chlorine only brings 7 electrons as the neutral form, so it depends how you do this counting. So chlorine is considered an X-type ligand. So any like chlorine, iodine, anything that just contributes 1 electron to the bond, that would be considered an X-type. And I'll just throw it in there. The other type, so you have LX and Z. Not to be confused with 2, but Z is actually means that it is taking electrons from the metal. So metal donating to ligand. So that's kind of less common, or you kind of see that in those funky scenarios. Let's see, so what is, so take a look at these 3 compounds. So we have, and these are all water as a ligand, so these are all neutral. And you have their charges there, so see if you can figure out their D count. What do we get for the D count of this vanadium hexaaqua compound. Yeah, so in this case, right, the waters don't do anything with the oxidation state, so they're what's called neutral ligands, right? And I drew them how they're attached, but I'll kind of show again. Right, so each of these oxygens, they have a total of 2 lone pairs, but then one of those, right, can donate. And so that's how they're bonded. And so that would be considered an L-type ligand, and it's neutral, right? There's no charge on water. So that doesn't matter. But then we do have an overall, right, 3+ charge just from the oxidation state of vanadium. So maybe it was reduced before, right? We don't really know how we got there. But if I ask for the D count, so it's 3+, so we can start back at vanadium, so find, right, where the neutral is, so 5, and then 3+, so lost 3 electrons. And so what does that leave us for the D count? I'm watching the chat too for answers. So D2, exactly. So let's look at that again, right? So it's, you just have to orient yourself on your periodic table. And so put these big numbers here if you need. I know every little periodic table is different, but just remind yourselves that these are the D counts of our neutrals. And so something else that we should practice while we're looking at this compound, and I didn't ask for it, but for the total number of electrons, and do people remember, like, what's the typical amount for transition metals? You might have learned this in, like, high school chemistry, what people say. So usually you're looking for like 18 electrons, but we'll find that that's often not the case for how many electrons you have. And so let's see how to count them. And so we're starting with, again, 3+ here. Neutral ligand, so I don't have to worry about any bookkeeping with there. And then so they're each donating 2 electrons, and so we have 6 of them. So 6 times 2 is 12, and then we have 2D, so this will be 14 electrons total. So now try that for the manganese and the cobalt complexes. So get their D count, and then see if you can figure out their total electron count. So do we get a D count for manganese over here? D5. I got it. Yeah, D4. So make sure you start at D7 for manganese, and then it was 3 plus, so 1, 2, 3, so D4. And then how many total electrons did manganese have? You can start with vanadium's answer, right? Because you still have 6 water ligands on there. Except now you have a D4. Yep, so 16 electrons. And this is kind of typical, so right, vanadium's kind of more early metal, so it makes sense why it tends to be not 18, kind of what you're looking for. Then manganese is kind of more middle transition metal, so that kind of makes sense where it's 16. And you see this a lot where either maybe they're 16 or 18 for their total electron count. That's pretty common. Or 19. And so now, do we get a chance to look at cobalt? So D6. And we can double check that. So cobalt 9 plus 3, so that brings us to 6. And then how many total electrons are in this system? So 18, at least 18 electrons on that metal center, which is what we care about. All right, last kind of 2 minutes of class, we'll demystify what the heck is kind of going on here. And so what's interesting, so if you break this down, right, you have this sodium 4 plus, and then all this is showing, right, is a dissociation. And so what this is showing you as well is it's telling us, right, that the sodium's just kind of there to balance out this -4 charge on our species that we really care about, this iron hexacyanide compound. But this also shows us kind of the location. And so this is called a counter ion, but then it would also be known as what's called outer sphere. And so by saying outer sphere, that means that it's not like directly coordinated to the metal, right? Like there's no physical bond between the sodium and the iron. It's just hanging around, right, just like sodium chloride. Same sort of concept, right? There's no physical bond between them. They're just held together electrostatically. And so that's really clear once you put it in water, and then it disassociates. So that sodium is just your counter ion. It's not in what I would call, right, the structure of your compound. And so your structure itself, and this is referred to then as like either your complex ion, or if you were talking about some sort of, if you for some reason had a sodium in there attached, then that would need to be noted, and that might be called inner sphere, some sort of inner sphere interaction, which happens sometimes with like magnesium, for example. Like usually that's going to be a counter ion, but sometimes you'll find a compound where that magnesium is part of the entire system, with like crown ethers or something, but that might make a magnesium inner sphere compound, in which case it is part. And so that's all that is showing, and so that leaves us with iron, and of course it's a 6, so that means that it's our classic kind of octahedral compound, what we expect, and each one of these cyano groups, cyanide, right, they have a negative charge, so these would be considered X ligands, and they contribute 1 electron. All right, we should probably stop there. So we'll continue on And so we haven't answered the question of where the pretty color comes from, but we'll head into that more. We'll go over naming, so we still haven't named formally, but then we'll get into a little bit of crystal field theory and explaining where the pretty colors come from on these compounds. All right, so I will see y'all Thursday. Don't forget pants. So I'll just remind you. So don't forget your pants for Thursday. And so I will see you all on Thursday. I forgot to print out the lab, but if anybody wanted it today, I can go make some copies. Do people want lab copies? No, no urgency. It's end of spring quarter. Yeah. All right, I'm going to go ahead and end the stream. Thank you all for being here. Unless there are any urgent questions, I'll hang around for another minute just in case, and then I'll end the stream. Otherwise, thanks again. I'll see everybody on Thursday.
Can I just turn on 25?
Oh, yeah.